Welcome. We will continue analysis of variance. So, I am writing one way analysis of variance. So, the word one way is coming from only one factor with different levels. Different means A levels. So, last class what I have discussed, that is also this one way ANOVA. Okay. So, we will see the same example, the calculation, and also we see that how ANOVA is used for hypothesis testing of the equality of different level means. So, let us see this. Last class you have seen what is the formula for computation of SST. You have a number of levels, you have n number of replication, you have individual observation Yij, everything is subtracted by their grand average and you make the square. This is what we have given. Now, this can be simplified to j equal to 1 to n, I equal to 1 to a, then Yij square minus y dot dot square divided by n. Okay. So, what are the differences? Yij, you know this Yij, but what is yi dot dot? Yi dot dot is sum total, grand total. What is n here in this case? I have a levels, each level n replication. So, n equal to a n. What is y dot dot? This is the grand total, total of all Yij. And then what if I write what is this? This is grand average, that I have discussed in last class. So, this is the second one. For if you use SST equal to this makes your computation easier. So, this formula we will use for SST. Now, similarly, you can compute SS treatment, but in SS treatment what I have said, you have n replication against each level, then I equal to 1 to a, different levels. So, every level you have average, then minus grand average, this square. This is what we have seen in the last lecture. This can be written like this, I equal to 1 to n, then y I dot this square minus y dot dot square divided by n, and here it will be 1 n square will come here. So, that means it is nothing but 1 by n, I equal to 1 to n, y I dot square minus y I dot dot square divided by n. Okay. So, that means every row total square, take their sum divided by n, and this portion is the correction factor, or I can this y dot dot square by n, that will be subtracted. Okay. These two you calculate, SST and SS treatment. Then SSE, simple subtraction, SST minus SS treatment. So, this is the formula we will be using. So, I am repeating the sum square decomposition, the total sum square, SS means sum square, equal to treatment sum square plus error sum square. This is SST equal to SS treatment. I am repeating this because this is very important, SSE, error. Okay. Now, another important concept is that what is the degree of freedom? DOF means degrees of freedom. When you are computing SST, what is the degrees of freedom you are enjoying? So, please come to the SS total computation. What I have written here? SS, in order to calculate SS total, you have n number of observations at hand. N number means AN, capital N. This amount of data you have, but for every time you have subtracted this grand mean, grand average. So, you have estimated grand mean, that means one parameter is estimated here, which is subtracted from this. As a result, what happened, as every time you are subtracting this, so what happened, you eventually in this computing this statistics SS total, you have n minus 1 independent observations for computation of this, one is lost. So, that means this equal to a n minus 1. So, what I mean to say, the degree of freedom for this is n minus 1, or you can write a n minus 1. Okay. So, it is something like this. Suppose I have given you x plus y plus z equal to 15. So, what is the degree of freedom you have in this calculation? You have 2 degrees of freedom. The reason is, if you write this 5, this 10, then this will automatically become 0. Same thing happens here. Same thing happens here. So long you will, as soon as you put n minus 1 number of observations here, the nth observation, capital nth observation will automatically be calculated. So, you have effectively n minus 1 freedom. Okay. So, now what about SS treatment? How much data you are actually enjoying when you are calculating SS treatment? When you are calculating SS treatment, you see that you have a number of observations, only this I equal to 1 that is varying. So, a number of observations, again this grand mean is computed. So, that also coming from this a number of means. So, 1 degree is lost. So, that means you have here a minus 1 degrees of freedom. Okay. So, then n minus 1 degrees of freedom here equal to a minus 1 plus this degrees of freedom also. What happened? The total degrees of freedom remains for calculation of error. Already here a minus 1 degrees of freedom enjoyed, here 1. So, what will happen? You have n minus a degrees of freedom left to calculate the error, and you see n minus 1 equal to a minus 1 plus n minus. So, that means not only the total sum square is divided into 2 parts like sum square treatment and sum square error, your total degrees of freedom is also divided into 2 parts. Then total degrees of freedom is equal to treatment degrees of freedom plus error degrees of freedom. Very, very important concept. Okay. Now, I will show you that the ANOVA table. Come to this slide. So, SS treatment, SS error by subtraction and SS total by this formula n minus 1, a minus 1, n minus 2, this degrees of freedom is there. So, you calculate another sum square which is known as mean square. What is this mean square? Mean square is the sum square divided by degree of freedom. So, that means your ANOVA table will be like this: source of variation number 1. In this example, how many source? One is treatment, another one is error, and then the total. Total is nothing but treatment plus error. Then suppose I want to know what is their sum square. So, sum square treatment, then sum square error, then sum square total. And you know how to compute this sum square treatment, the formula already given to you. Now, what is the degree of freedom? Degree of freedom for treatment is a minus 1, for this equal to n minus 1. So, this will become n minus a. So, total degrees of, for while calculating SST, degree of freedom is n minus 1, while calculating treatment degree of freedom is a minus 1, then remaining n minus capital N minus a degree of freedom for SSE. Then what is mean square? Mean square means that this is nothing but SS by DOF. So, SS means for the respective one. So, I want to know MS treatment. This will be SS treatment divided by A minus 1. You want to know MS error, which is nothing but SS error by degree of freedom. SS error by degree of freedom. Okay. So, in this ANOVA table, you see that everything is there. Apart from this, there is another quantity called F0. F0 is nothing but MS treatment by MS error. So, we are interested to know also another one, which is F0 equal to MS treatment divided by MS error. Okay. So, that means this is nothing but SS treatment by degree of freedom by SS error by degree of freedom. If you recall that in the when I talk about sampling distribution, then I have given you that SS, this one follows chi-square distribution with n minus 1 degrees of freedom. So, here what happened, SS treatment follows chi-square distribution with a minus 1 degrees of freedom and SS error with n minus 1 degrees of freedom, and this is the ratio of two, F0 is the ratio of two chi-square variable weighted by their respective degrees of freedom. If you know that F distribution, we say chi-square nu 1 by nu 1, then chi-square nu 2 by nu 2, where nu 1 is the numerator degrees of freedom, nu 2 is the denominator degrees of freedom. So, that is why this quantity is also, and then this will be nu 1 and nu 2, chi-square nu 1 and nu 2 is like this. Now, you got one quantity F0, which is that SS treatment by a minus 1 degrees of freedom and SS error by n minus a degree of freedom, then this will follow F distribution with a minus 1 and n minus a the numerator and denominator degrees of freedom respectively. Okay. So, this is what is given here. So, find alpha, I will tell you later on, but a minus 1 and n minus a. N minus a is nothing but a into a n minus a. So, that means a into n minus 1. So, now you have to do the hypothesis testing. What happened? You have computed F. Computed F is F0. How do you compute? Once you know MS treatment and MS error, you are in a position to compute, and you know how to compute SS from the data, then you will be able to compute this one. So, this follows theoretically, suppose this is this following F distribution something like this. So, this is our F distribution, PDF of probability density function of F. So, what we are interested to say that whether there is difference in the means of the different levels. So, if there is no difference, then what will happen? MS treatment and MSE will be equal. MS treatment and almost equal to MSE. What is MSE? It is error. This is a random one. The error what is occurring here, it is because of random. So, again that MS treatment, the different level effects also equal to random error effect, means there is no effect. That means the different means are not different. The means of at different levels are not different. Not different means are not different. Means at different level, treatment levels are not different. So, this is my H0. mu 1 equal to mu 2 equal to mu a. Other way I can write H0 tau y equal to 0 and H1 tau I not equal to 0. How tau I equal to, what is tau I? Tau I equal to mu I minus mu. Now, if mu 1 equal to mu 2 equal to mu a, this will be nothing but grand mu then, because mean of means this will be this. So, if mu I become mu, then tau I is mu minus mu, that is become 0. So, our H0 is no effect, H1 is there is effect. So, other way I can say, if there is no, so under this null hypothesis, this quantity follows F distribution. If H0 is true, this quantity follows F distribution. Okay. So, what we want then, so this is the F line, so any value possible, let from the theoretical side, so this may be far away from somewhere, we will create a threshold value for F. So, this one will be alpha. So, then this value is f a minus 1 n minus a into alpha. If that, this is known as the tabulated value. So, if your computed value f0 is greater than or greater than equal to tabulated value f alpha a minus 1 n minus a, then you reject null hypothesis. What is the null hypothesis? There is no treatment effect, or mean of the response variable at different treatment levels are not different, that is what is H0. So, from this you are in a position to say that there is the null hypothesis true or false. If it is false, reject null hypothesis. Okay. So, let us see the example. Same example here, ground clutter, differentiable low, medium, high, average, our three levels low, medium, high, mu 1 equal to mu 2 equal to mu 3, H1 they are not equal. Maybe at least one is not equal, need not be that all three are not equal, but at least H1 will be at least mu 1 not equal to mu 2 or mu 2 not equal to mu 3 or mu 1 not equal to mu 3. If any one or more of them satisfied, that is what is H1. When there is at least one pair which is different. Now, using ANOVA table, always what we found out that F value is 2.27, and if I consider alpha equal to 0.05, that means 5% error is considered, type 1 error is 0.05, then the tabulated F value is 3.46. So, computed F value is 2.27, which is less than tabulated F value 3.47. So, as computed value does not exceed the tabulated value, you cannot reject H0, fail to reject. Our decision here is fail to reject H0. So, that means there is no treatment effect, or if you change from data from clutter level from low to high, there is no difference. Okay. But you may not accept it because conceptually or from actual field you observe that there is a difference. If this is the case, then the data, what data we have used, data collection, either data collection is wrong or the data we have used, maybe the data from another experiment we have used differently. Actually, that is what we have done here. The original data is basically with two factors and with that one noise variable, that operator. But here intentionally what I have, the same data set we kept, but individual level factor we are here clutter level we are comparing. So, maybe that may be the reason, but whatever may be the thing, the procedure is like this. So, now see the another one, that power data, that is the each rate case. Here what happened, when we are doing all kind of calculation and finally making the ANOVA table, you see we are getting the computed F0 is 66.80 and tabulated one is again, if I consider this one, that a minus 1 is 3 and here error degrees of freedom is 16. So, 3 into 16 degrees of freedom, then we will find out that value is much lower than 66.80, and in fact the probability type 1 error is less than 0.01. That means in the second example case the things are coming somewhere here, this side this much error is there. So, if my threshold value is here and my actual the computed value is falling here, so that what does it mean? It is satisfying the second one. So, reject H0, that means the different power levels are affecting the mean each rate for the second experiment. Okay. So, thank you again, and it is again the Montgomery book DOE. Thanks a lot.